Why can small parameter changes cause system instability? Imagine a delicate house of cards. Just a tiny breath can make it collapse. In control systems and power systems, small tweaks can have a similar effect. Let's explore why tiny changes can lead to big instability issues. In electrical engineering, especially in control systems, the system's behavior depends heavily on its parameters. These parameters include things like generator control settings, damping coefficients, and inertia constants. When these are altered even slightly, they can change how the system responds to disturbances. The stability of a system is about its ability to return to normal after being disturbed. If the system is stable, it will settle back into a steady state. But if parameters shift just a little, it can cause the system's eigenvalues to change. Eigenvalues are numbers that tell us if the system will settle down or spiral out of control. In linear time invariant systems, stability is checked by looking at these eigenvalues. If any eigenvalue has a positive real part, the system is unstable. Small parameter changes can push these eigenvalues across the boundary that separates stable from unstable. This means a system that was stable can suddenly become unstable with just a tiny change. Why does this happen? Because the different parts of the system are interconnected. Changing one parameter, like the damping in a generator, affects multiple states and modes. Sometimes, these changes reduce damping and make oscillations grow instead of fade away. When damping drops below a certain point, oscillations can amplify and cause instability. Power systems are especially sensitive. Small disturbances like load changes or minor parameter tweaks in generator controls can cause voltage or frequency issues. For example, if the excitation or governor settings in a generator are adjusted slightly, it can alter how quickly oscillations die out. If damping becomes too low, these oscillations grow, leading to instability. Another reason is the shrinking of the region of attraction. This is the set of initial conditions from which the system will return to equilibrium. When parameters change, this region gets smaller. That means even tiny disturbances can push the system outside this safe zone, causing it to become unstable. Engineers work hard to optimize control parameters to keep the system stable. They adjust things like virtual inertia or damping controls to improve small signal stability. But because power systems are complex and nonlinear, predicting exactly how a small change will affect stability requires detailed analysis. In essence, small parameter changes can cause instability because they alter the system's dynamic response. They shift eigenvalues and damping ratios, making the system less able to absorb disturbances. This can lead to oscillations growing out of control or the system diverging from its stable state. Understanding these effects helps engineers design more robust systems that stay stable even when tiny changes happen.